particles is an amazing field of physics. It's vast, very vast, and I'm hopefully going to teach you some today. So, welcome back. This is my second video. My first one was, how long ago? Probably like nearly 6 months ago. I haven't really had any motivation to do any videos, but here we are. So, if we go all the way back to the late 19th century, it was believed that there would be some limit which you could break everything down to, but they didn't really know what it was. And so, with the discovery of the electron by J.J. Rutherford, the first model of the atom was comprised of, it was called named after the, I believe, British dessert plum pudding model. It's where you have a ball of negative charge and you have little bits of, it's a ball of positive charge and you have negative charges in there, and it's like a plum pudding. But I mean, it's a pretty bad model of the atom, if you can tell, and isn't accurate. And so we have the alpha particle scattering experiment that Rutherford did, where you fire alpha particles, what is an alpha particle? An alpha particle is very similar to a helium nucleus because is comprised of 2 neutrons and 2 protons, and it's this very high speed, very big in terms of particles, very big chunky boy. And if you firing loads of these at a sheet of gold foil, and what we found is that most of these alpha particles would pass through. So they derived this model here. And this model, now the atomic model or the Bohr model, named after the great physicist Bohr. And this is my website here, cranny.uk, and here, if you can see, is a lithium atom here with the red bits. I made this website over about 9 months ago, so I've forgotten which I put as the neutron and which one I put the proton. I believe the red was the proton, black was the neutrons, and then obviously these are the electrons. As you can see, this is quite inaccurate because the electrons are way smaller, and they are, even though they are a lot heavier though. I'll tell you more about what we call quote unquote heavy in a bit. What I mean is they've got more charge than in here. Electrons, they're not like this. They would actually be in a cloud of superpositions where they could appear at any point around this cloud. This is better only for, put it in here, a hydrogen atom, because it's only got 1 electron. So it's very easy to know where it's going to be because you're only looking about 1 superposition around a field on only 1 energy level here. And I think I will. So there's a reason why electrons appear at energy levels, and that's the Pauli exclusion principle. And that is that these can't exist at the same piece of space at the same time, because if it just breaks the laws of physics, and so they have to be at energy levels at certain points. Obviously, not orbiting like the Earth orbits the sun very differently, actually, but it's a very, very good way of modelling the atom. And my website can even do massive chunky atoms like uranium. Look at all those electrons. Ooh, it's massive. Anyway, and as we were talking about earlier, an alpha particle, this is denoted by the Greek symbol alpha. And it is there's many ways that alpha particles can form, but usually if we're talking about how we utilize it, this can be for nuclear fission, which multiple of these firing out millions and millions each second, causing chain reactions, mass amounts of heat, of course, is not the most efficient or the best way. That's nuclear fusion, but I'll go on to that more towards the end. This is our first form of radioactive decay. We have beta, funny enough, denoted by the Greek letter beta, where you can have an electron or a positron, or that released. And our final one is gamma decay. That appears in each one of these previous ones, but it's a really crap wave. But yeah, it's an electromagnetic wave. It's got one of the highest frequencies on the electromagnetic spectrum, one of the smallest wavelengths. I'm talking on the nanometer level. You can talk about it. Obviously, this is because this is particle interactions. And so we're going to talk about where gamma comes from first. So if we have a proton here, we have a antiproton. These, I've realised, I'm about to draw a Feynman diagram, which I'll explain as I do it. So a Feynman diagram is here. You have your time axis, so time, and here you have your space. What you can't do is you can't go downwards, because that means you're going back in time, and you can't do that. You always have to go forward. So if we have a proton, and an antiproton, these two will collide and they will form a gamma wave. What will happen later on is the gamma wave will decay into, guess what, a proton, antiproton. And if you wanted to know, I wonder how much energy this gamma wave here is going to be or needs to be, we can easily do that. And if you didn't know, that is by the very, very famous equation E equals mc squared. C being the speed of light in a vacuum, and that is that's around 3 times 10 to the 8, which c squared being 9 times 10 to the 16. M is your mass, and this won't be in kilograms, this will be in electron volts or mega electron volts, depends what you use it, and this is in joules, of course. It's energy, it's in joules. But we have, of course, 2 protons here. So let me get out my handy dandy data sheet. So I don't think you can hear it. So it's a lovely piece of card here. And the proton rest mass, we're going to ignore that these would have kinetic energy, but you know, we're talking about minimums here. 1.673 times 10 to the negative 27. Put that in brackets because some calculators are really weird. They like times this first. I don't know why. They're thinking it's bid mass even though it's a one number, which is quite annoying. Then we need to times this by 9 times 10 to the 16. And this equals the energy. Oh my goodness. Have I started a video without a calculator? Have I not got a calculator here? I've got my phone. I've got a calculator. That's not very good, is it? There, I found it. It was under books. I need to clean my desk. It's too cluttery. Get our handy dandy scientific calculator out. And we get 3. It's actually wrong here. Sorry about that. It's actually kilograms. This can also be in electron volts. Sorry. It's a Sunday as I'm recording this. Okay, I'm going to make a couple of mistakes because it is a Sunday. But we get 3.011 times 10 to the negative 10 joules. And so we want to convert that into electron volts. And so, knowing the equation, energy equals charge times voltage, we now know that from this equation that if we have the charge, which we use the elementary charge, which is 1.6 times 10 to the negative 19, and we're saying that this is our electron volts, and this is equal to 3.011 times 10. Oh, that's gone all over the place, hasn't it? All over the place. 10 to the negative 10 over 10 to the negative 9. Oh, 1.6. We can then get our charge, which is going to be very high because there is a lot of energy in protons. That is, that's a large number. So that is about 1,881 electron volts. Mega electron volts, sorry. Get my units right. Yeah. So that's more 1.881 giga electron volts. And that is in mega electron volts. That's a lot of energy, that gamma wave. So if we wanted to know now what the we wanted to know that by I do wonder, what would the wavelength or the frequency of this gamma wave be, you know? Well, obviously we're not going to want to use this, as this is a completely different unit, so the joules would have to go back over to here, get this piece of data here, and use that. So I'm not going to go into too much into what Planck's constant is or where it comes from, but instead I will probably do a video on waves later on another time. I was initially going to do a video on waves, but I decided I hate that topic so much that instead that part of physics so much that I am instead going to do particles because it's my favourite topic in physics. I had to get the formula out real quick. Okay, so the energy of a photon is equal to Planck constant times the frequency, which equals the Planck's constant over the speed of light over lambda. Quickly, I'm just going to derive that, V equals F lambda, and we know from that if we sub in V over lambda, so it's essentially just this. You can easily derive it. Anyway, let's say I want to find, do you know what, we'll go with wavelength. So wavelength equals hc over E. So h is equal to Planck's constant is equal to 6.6261 times 10 to negative 31. I probably should round that to 6.63 times 10 to negative 31. And then we times that by 9 times 10 to the 16, and we do that over our initial energy, our energy from over here, and that should give us our wavelength. Remember to put the brackets in my calculator, or it will probably try and do something else. No, I don't know. I don't trust calculators. I honestly hated the calculator GCSE exam. I much preferred the non-calculator. So we've actually got a pretty large wavelength for here. I've no idea why. Check my that's interesting. So we've got a wavelength of 1.9817 times 10 to negative 4 here, and that would be in meters. I've no idea why it's large. Of course, if you can see here, if we subbed h under energy, which is quite high here, to Planck's constant here, which is quite low, you're going to get a very, very high frequency, and that's what gamma waves are. Very, very up at just loads, very high frequency. But I haven't really gone on what photons are. Well, photons, they are a carrier for the electromagnetic force. Always getting into the maths first instead of the explanation, so if you were lost there, I'm very sorry. get myself carried away. So, oh my god, that was awful. It's going to draw a sine wave. That's a bit better. Let's finish it. If I do green here, oh, that's awful. They are they're perpendicular to one another, the electro and the magnetic field, and they're things like light, microwave, ultraviolet, gamma rays. These are all carried by the electromagnetic waves, photons. The electromagnetic force is a virtual photon. I've already shown you another one Feynman diagram. Let's show you another one. So let's say we're talking about beta decay here, because we've already done alpha decay. Let's say if we have a neutron that decays into a proton, and that is what caused beta decay, this decay. All things eventually will decay into a proton if they're a baryon. I believe that. I should probably put a bit of the comment below if I get that wrong, if I get anything wrong, because I'm human and there's a lot to this topic. I love it so much because there is so much to it. But if we have a neutron and it goes positive, that means that we have a new exchange particle called the W boson, and the W boson is the exchange particle for when we have like a baryon here. I'm going to get this wrong, aren't I? I should probably get out my notes for because there is so much to baryons and hadrons. Well, they're the same thing. They are an exchange particle, and you have W boson plus, W minus plus. But the amazing for this boson, I forgot his first name, pardon me. He is very big in particle physics. You have the Higgs boson field. This is very advanced. Basically, 1% of all the forces in the universe is the Higgs boson field. But nothing would have mass without it. Anyway, I'm getting sidetracked, aren't I? As you can see, still going through time. This then produces an electron and this new particle. Ooh, what's this? Well, this is an amazing, wonderful particle known as the anti-electron neutrino. That was a big oopsie in physics. Now we call the one that is released with an electron anti-electron neutrino, and the one that's released with a positron, or the beta particle, the one where it's a e to plus, we call that a electron neutrino. And the neutrino, they don't react to electromagnetic force. They're literally like they've got nobody's business. And so even though the sun emits like 6 billion every second, even then, we built this as humans, this massive ass pit, massive ass. Don't know why one note's doing that, but massive ass pit. We had sensors all over the place, and you can see there's these like physicists, and they're on boats, going over because with like this heavy water, and only one of the sensors detected a neutrino. But these were theorised because, with beta decay, there was this bit of energy, and you never want to break the conservation of energy. That and thermodynamics, never want to break it. So if you do, goodbye, goodbye. That's what we're talking about. Goodbye. But these were theorized to also be released. Of course, a gamma wave here is also released, but we don't really show that. So I'm going to go into more types of particles. So we have quarks, and if you've ever wondered, what on earth is going on in the neutron, the proton? So we call neutrons and protons, we call those baryons, because they have three quarks in them. And then if you want two quarks, they're called mesons. And these are all hadrons because they have quarks. These are all called hadrons. So they have quarks. And then we have leptons. This is your electron, your muon. I swear to God, if someone makes a mewing reference, and your tyon. This is basically a fatter version of the electron. This is an even fatter version of the electron. So that's just your mum, basically, in terms of electrons. I hope this is very nice and relaxing. Sorry for insulting you, but funny. Anyway, so you have protons, neutrons. You have way more, but I'm not going to go into those because that is way too depth. Mesons, you have your pion and your kaon. Anyway, so if we're talking about a proton here, it's got a up quark, and let's talk about the flavours of quarks first, because I don't know why I went in straight in. Flavours. It's a lot of ice cream flavours, basically. So you have up, down, side to side, left or right. No, we don't. Fortunately, you don't have the char slide quark. Top, bottom, strange, charm, and finally, but not least, the party rock anthem. Okay, there's no such thing as the party rock anthem quark, unfortunately. But up quark, 2/3, top quark, 2/3, charm quark. This is charged relative to the electron. Strange quark, -1/3, bottom, -1/3, down, -1/3. And you want to make either -1, 0, or 1. That's what only particles can have, because you can't have fractional ones. That's naughty, it's not allowed. So here, with the proton, we'd have up, looks like a muon, and down. And in between them, keeps them together, ironically enough, is called gluon. And neutron, we have down, down, up. I've just realised I haven't talked about the strong or the weak force. Can't believe it. You know what? That is criminal. I've talked about particles and I haven't talked about the strong or the weak force. So, we're quite basic here about the strong force quickly, but I should probably talk about it. The strong force that we quickly sketched the axis here. The strong force, if we talk about newtons. What? I've tried to. Sorry, I have beef with OneNote. Here we have the Pauli exclusion principle. Because if you get closer and closer to these, you know, proton and neutron get closer and closer together, you know, the force between them is so huge, it's mental. Then this is when they get further apart, it's when the electromagnetic force kicks in and kicks them out, gets them gone. But there's also weak force interactions. Got the weak force as well. Strong force. Funny enough, guess what? Strong force is one of the strongest forces in physics. Weak force is quite weak. But the if we're talking about, I'm going to give an example here. As I don't know how to draw the graph, unfortunately, if there is a graph. If we have what we're talking about here, a kaon. So a kaon is created in a particle accelerator. It's when you bash and you throw it on into a neutron, just bash them together. You get a kaon and a sigma particle, but I can't be bothered to talk about sigma particles. A sigma particle denoted by K, but anyway, and this kaon, this is held completely together by the strong force, but it will decay over time, and it's very strange, and that's where the strange quark comes in, because it's very strange. It lasts for very long, and I'm talking, it's just like, for a human, it's like living only like 100, 120 years, it's like a kaon, and that's 22 microseconds. And that's when it gives in to the weak force, which leads it to decay, and then just decays into a bunch of what we call long-lasting particles, which are like pions up here, 2 quarks, 3 quarks, and it just decays into some pions. So, from that, I haven't finished my particle here, sorry, but also in particles, quarks have colours, but I'm not going to talk about it, and it's not like colours, but it's basically, oh yeah, well we got RGB, there's another type of energy, they charge they hold, but anyway, if we talk about mesons, because I've done like the 2 most important like baryons, we talk about mesons. If we wanted I'm going to see if I can remember this diagram, I believe. So if we have charge, strangeness, going for charge. Oh, this can be very interesting to try and, oh yeah, look at that. Strangeness. I'm not going to do it from memory, I'm going to copy this diagram out. We have the negative pion here, the neutral pion, and the positive pion, and we have neutral kaon here, and the positive kaon here. We have the negative kaon here, and a anti-kaon here. I believe that's it, but it's quite a... Thanks to one of the guys, of the 2 guys, one Japanese guy, one American guy, who came up with the kaon for that amazing diagram. I'm joking, both amazing physicists, probably do more than whatever I'll do. Anyway, if we're trying to make a neutral pion here, it's very, very easy. It's just a up quark, which I'm going to label as this, and negative up quark, down quark, up quark, whoopsie, up quark, then a up quark, down, down. I just did accidentally make the pi negative, which was is a negative down and a up. So, and then if we have a kaon, oh yeah, of course you can do this with kaon, K negative, you have a up quark, but then you have the strange quark. Oh crap, no, it's a up negative, sorry. K0, you have strange quark. Strange, very strange. Oh, I had realised, I think I've got that the wrong way around. I think it's supposed to be strangeness up. Whoopsie. As you can tell, I don't like this this diagram's quite hard to remember. I think it is strangeness up. And then it is charge. Yep, it makes more sense if you got negative here in one. Silly old me. Anyway, K2, we have the K positive, which is strange up, and there you've got some very interesting particles. Love the kaon, love the strange quark. Anyway, let's say now we wanted to do beta decay, but with quarks, and we can. Look at that. I think I'll do proton to a neutron this time. You can see the decay as one of the quark changes. W plus boson, and we get a beta particle. That was a lovely beta. Look at that. That was beautiful. That was absolutely beautiful. And we get an electron neutrino. That is our Feynman diagram there. But to finish this video off, as I think I've got over a lot here, like, whew, that's a lot. There's quite a bit of maths here. It's very famous maths, to say the least, but also have, I didn't mention about baryon numbers. If we go back to here, we have, go to our strange has 1/3, 1/3, well, actually not sure about 1/3, 1/3, yeah, you get the point. Got to mention that, whoopsie. Sorry. Of course, I could go into more, I could go into de Brueghel's wavelength for energy levels, but I think I've probably baffled a lot of minds already. But I also forgot to mention, I'll pick up some things I forgot to mention. So I forgot to mention about cloud chambers. I have a absolutely terrible box here, but if you have a cloud chamber, it's basically a bunch of alcohol vapours, and you put some very strong magnets here, electromagnets. You can then see different particles. So heavier will have a longer, and so if it's got more charge, it's going to have shorter, so it's going to be pulled in more by the electromagnetic force, but weaker charges are going to be go further out. And that's what you see in a cloud chamber. You also see like annihilation here as well, when and also creation when you have a gamma wave coming in, and it creates, you know what I mean. But I'm going to finish off with nuclear fusion, because it's one of the best things that are going to come out of particle physics, or most for the common man at least. I think the common man likes this, really cares about the standard model that much. But obviously this has been a quick gloss over everything. I surely hope nobody is revising off this, because it would be absolutely terrible revision material. Go to somewhere like Physics Online. Anyway, you have tritium, deuterium. Deuterium is proton and a neutron. Deuterium is 2 neutrons, 1 proton. And if you manage to smack these together, you create fusion, and this is what happens in the sun. That's why the sun's so bright, generates so much energy, because this is going on as we're speaking now. Loads, even other reactions as well. It's mental. And so if you do this reaction here, you can get these to bond together. You create a helium atom, have an extra neutron as well, and you have tritium as well to left off with it as well, you know. But the problem is, if fusion was this simple, doing it now, you know, CEO of Shell, he'd be pooing his pants because he's that scared. And that's what he does. That's what all these oil companies are terrified of. They're all terrified of fusion. Makes them keep themselves up at night thinking of fusion, you know. It's so terrifying for them. Anyway, you've also got deuterium and helium-3. I'm not going to draw helium-3 because I don't know how to draw helium-3, sorry. But you have, but there's multiple types of fusion. You have magnetic inertia fusion. This is what the French use. They have massive like magnets underground where they use the magnets and it's smashed together these, you know, these atoms. Not atoms, sorry, isotopes. Whoopsie, don't get at me. Don't kill me, please. I know that the hydrogen isotopes. Anyway, these smashed together. You also have laser as well. I think it's the laser inertia fusion. This is the fusion that this research institute in America came up with. They made 3 million joules, and they only put in 2 million. See, that was the thing for a very, very long time. I remember it was kind of weird because on that same day, I was going to a funeral like this, and it was like so weird. It was like this feeling of euphoria, of like amazement at the progress, because this was the first time in history that fusion had generated a surplus. But it did that in the same time it took light to travel basically about a meter. So essentially this, it travelled in as you know, power, energy over time. So you put 3 million, should read it to the 6, but hey ho. Pigeon just flew into, sorry if that showed up, a pigeon just flew into the window. Anyway, that's an amazing amount of power, isn't it? That's mental, the amount of power that I generated. If we could sustain this for so long, we could power the world with fusion. It'd be mental. Also, you have power in, power out, and this is this Q number, and this Q number here, you want to get it up. So for that generator to be 1.5, which is of course the first time ever we got it greater than 1. And let's work out this power here real quickly. just realised that's 9 times 10 to the 12 watts. That's mental. We can even work out how many electron volts it generated if we wanted to, but I'm going to be quite real. That's going to be a massive amount. That's going to be a massive number, and I can't be able to work it out. But fusion, the future of it is magnificent. I've got one more thing to say. Interesting thing: leptons, they go under polar exclusion principle, but bosons and photons, bosons, unlike leptons, they don't. So you can have loads of things. I mean, if bosons follows the polar exclusion principle, then the world would be a very interesting place. But I'll leave it there. Yeah, I'd thank you for watching. If I've missed anything out, please tell me in the comments below. If you'd like me to do another video, I've got a bunch of video ideas. This is probably going to be, for a while, my last like really technical one. I've got a couple of other like more fun ideas other than physics, because I don't want to just be making physics content 24/7, or somewhat related physics content. But I hope you enjoyed. If I did anything wrong, if I calculated anything wrong, or if I said anything wrong, please tell me, because I'm human. Obviously I don't get 100%, I get 70%, 80% on all my physics tests. So I am human. So please tell me. Have an amazing day, and or night, or morning, whenever you're watching this. And I hope you feel ever more relaxed by the physics, and I hope you have a good, goodbye.